Good evening to all. Welcome to the 11th live session on this payment materials. In today's discussion, we will be discussing about the assignment questions of the last week, followed by the summary of this week level lectures. And we will also solve few numerical questions regarding the week level lectures. Week 10 assignment questions. In the first question, it was asked that which are the key points of balanced mixed design. We know that we have four approaches in the balanced mixed design. So what are the key points of that? Here the first option says that incorporate performance testing that addresses multiple modes of distresses development within the payment structure. Yes, we already have the Marshall mixed design. So in addition to that, we wanted to incorporate the performance testing. So this is one of the key point. In addition to that, have four approaches. Yes, we have four approaches for balanced mixed design. And third option is approach A and B are conservative designs. Yes, approach A and B are conservative designs because we still satisfy the volumetric parameters. In addition to that, we try to satisfy the performance parameters. Therefore, it is a these two approaches are more conservative designs. So, all of the above is the option. In the second question, which of the following is a simulative type of test method? Now, in order to understand the performance of the asphalt mixtures, we have fundamental and simulative type of test methods, and also we have empirical type of test methods. As we all know, Marshall test is an empirical type of test method. So Marshall test is not an option, and also the indirect tension test. So wheel load test and repeated load creep test are the similar type of test method. If we specifically wanted to discuss, wheel load is a more simulative type of test method. This repeated load test, we usually get the fundamental information, though it is a simulative type of test method. We get the fundamental information regarding the mixtures in the repeated load creep test, whereas in wheel load test, we just get the pass or fail criteria. When I say fundamental information, that is the stress strain behavior of the material when it is subjected to particular test conditions. So this stress strain behavior will not be obtained from the output of the wheel load test, but it can be obtained from the fundamental test like repeated load creep test. Question: resilient modulus test is a ratio. We know how do we determine the resilient modulus. So we assume that after a particular number of load cycles, the amount of plastic strain in the asphalt mixture remains constant. Thereby the elastic strain or recoverable strain is the strain we would be considering. So if we wanted to determine the resilient modulus, the stress would be the deviatric stress, that is the net stress which we are applying on the sample or the material, and to the recoverable strain. So the ratio of deviatric stress and the recoverable strain is the resilient modulus. Which of the following statement is true? Dynamic modulus describes the material property. Yes, as we have already discussed in the last week, dynamic modulus exclusively describes the material property of the particular material. Resilient modulus quantify the material response to varying loading conditions. Yes, the specific purpose of resilient modulus is it actually quantifies the material response to varying load conditions. And option C says that both defines the material property and responses to varying load conditions. No, this is not the correct. And the option D says that both are the fundamental type of test methods. So the option A, B and D are the correct options. Which of the following parameters are used to quantify the rutting resistance of an asphalt mixture? So if you see the options, the first one would be ratio of Marshall stability and the flow value, which is nothing but the Marshall coefficient. Yes, this is one of the empirical ratio parameter using which we can actually understand the rutting performance of the mixture. In addition to that, the rut depth using any simulative or fundamental test methods, and also the flow number which we observe from the dynamic creep test or cyclic compression test, and also maximum permanent shear strain. So all these are the parameters to quantify the rutting resistance of asphalt mixture. Soundness test of cement is carried out using which apparatus? If we see the options, we know that blade method is actually used to understand the fineness of the cement. So option B is not the correct. And also this Vicat apparatus we use to understand the initial setting time and also final setting time of the cement. So Lee-Chatelier apparatus and also the autoclave method. If we could remember, we have a cylindrical type of brass ring in which we usually place our cement and we subject this to the heat cycles and also in the water bath and also drying conditions. We observe the expansion of the material. So based upon that we understood the soundness of the cement. So these are the two test methods. Which compounds are responsible for controlling the strength of the cement? We know for early strength, tricalcium silicate and also for late strength, dicalcium silicate. These two are main components that are responsible for the controlling the strength of the cement. So C3S and C2S. In the absence of gypsum, which compound is responsible for flash setting? We know that gypsum, if it is absent, the aluminate which will be reacting with water very quickly and it will tend to the flash setting. So in order to retard that process, we usually add the gypsum to the cement. So especially tricalcium aluminate, which is C3A, is responsible for flash setting if we do not add the gypsum. Higher amount of calcium hydroxide leads to. We know having calcium hydroxide in surplus amount will lead to the disadvantage in the cement properties. For example, this calcium hydroxide, whichever is extra present in the cement, when that is reacted with the tricalcium aluminates and or silicates, they will be forming, in the presence of sulfate, they will be forming calcium aluminate silicates. These are very much dangerous to the durability of the concrete mixtures or the any structures, especially in the marine conditions. Thereby, in order to avoid the sulfate attack, we usually wanted to reduce the amount of calcium hydroxide in the cement. So this higher amount of calcium hydroxide would lead to the sulfate attack in the concretes, especially at conditions where the concrete is subjected to the higher moisture contents. Which compounds are responsible for controlling the setting time of the cement? As we have already discussed, these aluminates are the one of the major compounds which would be setting very quickly if we do not add any kind of gypsum. Thereby, this tricalcium aluminate and C4AF, C3A and C4AF, these two are the responsible for the, this must be responsible for the setting time. So if we come to the week level, so during these week lectures, we have discussed about the types of cements that are present and also the additional materials which are called as pozzolanic materials and also geopolymers, and in the last lecture we have discussed about the PQC mixed design. So if we see about the types of cement, as we have already understood the basic mechanism or the process of preparation of cement, where we need the calcium and also silicate as the raw materials, and these when subjected to the higher temperatures, which would be formed as a clinker, and at the end those which are finely grinded will be added with the gypsum, and we will be obtaining the cement. So the process would be same in any kind of cement, but the amount or the proportion of the raw materials would be varying. So based upon the amount of raw materials and the kind of raw materials and also the targeted desirable properties, we have different kinds of cements according to the Indian standard specifications. For example, if you could see, these are the four types of cements. One is ordinary Portland cement OPC, and another is a Portland pozzolana cement PPC. Third is the Portland slag cement PSC. Fourth is the sulfate resisting cement SRC. So all these four, one thing we have to observe is, let us say this is a normal kind of cement which we all have already known, which is known as OPC. But in order to produce this remaining three, PPC, PSC and SRC, we still use the basic OPC, but to that OPC we do the blending. When I say blending, we will be adding either extra pozzolanic materials or admixtures. So based upon the amount of or proportion of the remaining materials, our kind of cement would be named differently, as we have mentioned here. So if we consider the ordinary Portland cement, where in general in India we have two types of ordinary Portland cements. One would be OPC 43 and OPC 53. So the main in the process of preparation of ordinary Portland cement, so we subject these raw materials to a higher temperatures of around 1500 degrees. So in the same way, the energy consumption is high, and also the higher heat would be produced in this process. So the environmental pollution would be more in this, because whenever these OPC or cement reacts with water, so CO2 is the output or the byproduct in all the end process. So this carbon emission is one of the main environmental disadvantage while using the ordinary Portland cement. This is one of the reason why we wanted to go for the alternate materials, so that we can eliminate the emission of carbon dioxide into the environment. Thereby we got the PPC. So the raw material proportion in the PPC would be, the basic component would be ordinary Portland cement. In this ordinary Portland cement, in addition to the raw materials like calcium and silicate, we use the 15 to 35% of fly ash. What is this fly ash? Fly ash is a pozzolanic material. This fly ash consists of already some siliceous or aluminous materials. Then you may say that because in the OPC, the raw materials are siliceous and aluminous materials only. So we are saying that these when reacted with water, because of the hydration, we produce CaOH twice and also CSH gels and also the carbon dioxide. So these CSH gels are the ones which are strength properties, which are giving the strength to the cement or concrete. So we might think that whenever we have siliceous and aluminum materials, we would be actually obtaining the CSH strength related properties. So though fly ash has the siliceous and aluminous materials, we will not be obtaining the strength related properties from them, because no cementitious properties, because the amount of calcium or silicate in the fly ash would be very less, and it also depends upon the source from which we have actually obtained this fly ash. So that it would be very minor in proportion, the cementitious properties, but in major, if we wanted to get the cementitious properties, usually this fly ash, where it is finely divided, so this finely divided fly ash, it will actually react with the calcium hydroxide. One basic thing we all have to remember is, how come this PPC and the pozzolanic cement and also sulfate attack cements or Portland cements, all other cements are different from the ordinary Portland cement is, ordinary Portland cement byproduct is calcium hydroxide sometimes and also the carbon dioxide. So we know that having higher amount of calcium hydroxide will lead to the sulfate attacks and also durability will be reduced. So we have to reduce the amount of calcium hydroxide in the after cement hydration, and also we have to reduce the carbon dioxide emission. So in order to reduce this calcium hydroxide, we have to reuse the calcium hydroxide, because initially when there is a calcium hydroxide production, we have to reuse that in such a way that the amount should not be accumulated. So in order to reuse this calcium hydroxide, and also we have to get a cementitious strength properties after reusing this calcium hydroxide. That is the reason why we are using all kinds of pozzolanic materials like fly ash or GGBFS or any other pozzolanic materials or admixtures, so that we are going to react with this calcium hydroxide to form some cementitious compounds. So here the finely divided fly ash, when it is reacted with the calcium hydroxide, this calcium hydroxide usually obtained from the hydration of OPC. So initially we already have OPC. This OPC will be reacted with water and it will already form CaOH twice, which is calcium hydroxide and carbon dioxide. So this is initial stage would be continued. This calcium hydroxide whichever is formed, when they have mixed with the fly ash, they will be forming some cementitious compounds. These cementitious compounds, which are nothing but the CSH gel compounds. These are the basic compounds to give the strength for the OPC. So usually this fly ash from where we obtain it from the combustion of coal in the thermal plants. So the main purpose here is utilization of calcium hydroxide from the hydration of OPC. What is the purpose of this? It improves the durability, because we are eliminating the sulfate attack and also strength would be increased, the permeability would be reduced. How does the permeability would be reduced? Once, as we discussed in the last class, let us say if we have calcium hydroxide, so this calcium can be dissolved in water in future. If there is a lot of accumulation in the concrete, so this can be dissolved and the pores would be formed at the place of those calcium compounds. So in order to avoid that, we have to reuse the calcium hydroxide and convert them into the CSH products. Thereby using PPC or pozzolanic materials would actually reduce the permeability, thereby increases the durability. So these PPC materials or PPC cement would be more beneficial in hydraulic structures, because in hydraulic structures the concrete would be directly in contact with the water. So there is a higher chance that the sulfur would be attacking much into the concrete. So and reduces the alkalinity and resistance to corrosion. For example, always alkalinity is disadvantageous to the corrosion. For example, if we see the salt NaCl and also any NaOH, so all the alkaline solutions, if they are in contact with iron or steel or any of the material, they try to make the material to corrode. So we have to reduce the alkalinity so that we can avoid the corrosion. So by converting the CaOH to ice or calcium hydroxide into CSHs, we are actually reducing the quantity of the cement or concrete mixture. Thereby, we are also increasing the resistance to corrosion. In addition to the, there is another kind of cement which is called as Portland slag cement. The difference would be here the pozzolanic material is granulated blast furnace slag. So we already have the clinker. Clinker is a combination of raw materials when they are subjected to higher temperatures around 1500, and to that clinker we add the gypsum. We know till now we will get the OPC. To this OPC we add granulated blast furnace. So this slag, how do we get this slag? We usually obtain this from the iron manufacturing unit. So whatever we have, limestone, coke, when it is heated to higher temperature, this will form something called as molten slag. So this molten slag, when it is at higher temperatures, will be subjected to water spray. So when it is subjected to water spray, it will be formed into a fine sprinkles. So those will be collected and further grounded, which we call it as slag. So this slag actually reduces the heat of hydration. As we have advantages from the PPC, we have same kind of advantages from the Portland slag cement also. And the last type of cement is sulfur resistant cement. So especially those structures, marine structures which are more susceptible to the sulfur attack. So in those places, so what is the problem? Whatever the sulfur present, that will be reacted with the calcium hydroxide. Then we get a product called as calcium sulfate. This calcium sulfate is very much dangerous to the structures. Why? Because these calcium sulfate will be reacted with the tricalcium aluminate or tetracalcium aluminum ferrate. So the C3A and C4AF will be reacted with the calcium sulfate and they will be forming a compound called calcium sulfoaluminate, and this calcium sulfoaluminate usually increases the volume of the structure than the original. So when you have designed a structure for a particular amount of volume and after a few cycles of subjecting to the water and due to this sulfate attack, so this volume would be increased. As the volume increases, it would be prone to the cracking. So in order to avoid that cracking, the main purpose is we have to reduce this calcium hydroxide that is present. So this otherwise would be affecting the durability of the structures. So as we have discussed, this calcium sulfate whichever is formed from the calcium hydroxide usually reacts with the C3 and C4F. So whatever the cement that is having the lower percentage of C3A and C4F, those cements we can actually call them as sulfur resistant cement. So in addition to the types of cements as we have discussed, where we were using different kinds of pozzolanic materials like fly ash, slag. So we also have different kinds of admixtures. So let us discuss few of the admixtures and how they are going to change the properties of the cement. One of the admixture is the silica fume. So this silica fume or SF is usually produced from the alloy metal production or silicon metal production. So what will happen is in the silicon metal production, there will be a exhaust gas. So in the industry, we could have seen some after the metal production here, let us say, whatever the extra gases, they will be sent through the exhaust. So those gases will be producing the ions like SiO and also aluminum. So these things, when they are they are coming in contact with the oxygen, they will form SiO2. Let us say this SiO2 is collected from the exhaust gas. So this SiO2 in the condensation, that means when we compress into a chamber, it will form small droplets. So these small droplets will be collected into filter bags and we name them as silica cube. So what is the main feature of this silica fume is they are very fine in size and they have higher surface area. When I say higher surface area, they have the surface area. So we need to understand that when the surface area is 100 times more than the cement, that means it actually requires more amount of water to hydrate, because if we are not able to provide the amount of water required for the hydration, then we will not be obtaining the hydration products. If we will not obtain the hydration products, then strength will not be obtained. Thereby, higher the high surface area, higher would be the requirement of water. So this silica fume, what does it do? It actually reacts with the calcium hydroxide to form CSA gel. So just like the pozzolanic material, how they used to react with calcium hydroxide and forms the CSA gel, in the similar way, the silica fume reacts with the calcium hydroxide to form the CSA gel. So one of the disadvantages is it actually demands higher amount of water content in the cement hydration process, and it is recommended to use 3 to 10% in the doses, and it also increases the strength and reduces the permeability, especially when we wanted to produce the higher strength concrete. So then we would be using this, and it is a kind of costly. It reduces the workability, thereby necessitate the use of the super plasticizers. Why does it reduces the workability? Because let us say if you are adding the water to cement ratio in usual contents, but your silica fume, which is having higher surface area, it actually demands higher water content. If you are not able to provide the required amount of water content, then whatever the cement particles present, they will not be having the sufficient amount of lubricant to move in a easiest manner, which is nothing but the workability. Thereby the workability will be reduced if we do not have the sufficient amount of water. In those cases, you cannot keep on adding the water, because that would be again disadvantageous to the strength of the cement. Thereby, if we wanted to have the better strength but also wanted to have the better workability, in those cases we will be going for the super plasticizers. So these super plasticizers, so it is exactly like the emulsion we have discussed in the bituminous mixtures in the same way. So temporarily we would be having the plastic state of concrete, thereby workability can be achieved for the construction or transportation, whatever the duration be required. But after few amount of time, this effect of super plasticizers would be reduced, thereby the strength can be obtained. So just like the way we have silica fume, we also have metakaolin, which is another type of pozzolana material. So this is highly reactive pozzolana. So calcination and dihydroxylation of China clay. We know what is the calcination. What do we usually do in the initial process of cement production? We have the calcium products and also silicon products. These will be subjected to higher temperatures. When they are subjected to higher temperatures, whatever the moisture and all will be evaporated. It is around 1500 degrees, and that process is nothing but the calcination. So here, if we have a China clay, and if we subject that China clay to the calcination, so the kind of material which we observe would be metakaolin. So this metakaolin is also having higher surface area than the cement. But the surface area of metakaolin is lesser than the surface area of the silica fume. Therefore, if we discuss about the order, silica fume is having higher surface area, followed by the metakaolin, followed by the cement. So, what is the major difference? For example, here we are saying that we are also following the calcination process of the clay. So, the only difference is in usual OPC production, during the calcination, we use higher temperature degrees around 1400 degrees plus. But here in this process, we will be using the temperatures in the range of 700 to 900 degrees only. So, this metakaolin, when it reacts with the calcium hydroxide, it also forms the CSA gel. So, if we remember, the main mechanism in all the pozzolanic and also admixtures is we have the excess amount of calcium hydroxide after the hydration of the OPC cement. That calcium hydroxide somehow needs to be in reaction with the pozzolanic or admixtures. Thereby, it should form the calcium silicate hydrates or CSA gels at the end, because these are the cementitious or strength related properties for the concrete or cement. Thereby, this increases the strength and durability and reduces the permeability. So, what are the plasticizers? As we have discussed previously, let us say the silica fume is having higher surface area, which is 100 times more than the cement. So thereby workability would be more issue if you are going to use the pozzolanic materials like silica fume. In those cases, in order to improve the workability, so or in order to improve the water content as at least temporarily, so that we can work with the concrete until we place them in the field. So we have to use the admixtures like plasticizers. So calcium, sodium and ammonium, these related compounds are mostly used. So it is recommended that 0.1 to 0.4% by weight of the cement and up to a maximum of 1% as per the IRC 44 2017 in the India, and 5 to 15% reduction in mixing water. So the advantage of adding this maximum 1% of plasticizers is, as you add 1%, you have a advantage of reducing 5 to 15% of reduction in mixing water. That means even without adding lesser addition of 15% of water also, we can still achieve the workability required. So what is the mechanism of these plasticizers? What does they do? So usually you have the cement particles. Let us say this is your cement particles. So when I add the plasticizer, what happens is this plasticizer will come and sit on the surface of the cement, which is nothing but the adsorbed on the surface of the cement. Then what happens? So you have all cement particles all around, and around each cement particles, now you are observing that there is this plasticizer which is actually adsorbed on the surface. Now all the surfaces are red, that means plasticizers. So these plasticizer used to get repel. So what happens when they repel? They actually wanted to move in the different directions. So this will be moving to this direction, this will be moving to this direction. Thereby we are actually eliminating the coagulation or flocculation. So we are making the cement particles to be segregated, we are not making them to come closer. Thereby we can easily mix. So cement particles, they will repel, and thereby the flocculation can be prevented. So this sheath around the cement may retard the hydration process with time. So for example, in the initial period it is okay because you need the workability. Once you completely mix and your mixing process and everything is done, so during that time usually the hydration process may retard a little bit, because how does the hydration occurs? Hydration occurs when the cement comes in contact with the water. Currently what has happened? Currently uh, we have actually a sheet around the cement particle. So if we have a sheet around the cement particles, actually they cannot able to come into contact with the water directly. Thereby, temporarily this hydration process may return. And as just like the plasticizers, we have something called as super plasticizers. As the name suggests, previously the maximum amount of reduction in water would be around 15%. Whereas if you wanted to reduce the water content predominantly like 30%, then we need to go for super plasticizers. These super plasticizers are powerful dispersing agents. Up to 2% by weight of cement can be used in the production. And the third type of admixtures are air entraining admixtures. Why do we even need to go for air entraining admixtures? For example, now you have concrete. So let us say if you have concrete, what happens in the areas like Jammu Kashmir, where the environment would be of very much cold, this freezing thawing cycles are very much common. That means in winter, let us say whatever the pores inside the concrete, if there is some water or something that gets frozen, then after few amount of duration or after few seasons, what happens? Let us say in the summer, that would be converted into the liquid. And again, what happens in the winter? That would be again frozen. Thereby, when it is getting into frozen, the volume would be increased, which will again lead to the bulking and it will be leading to the cracking of the concrete or cement or any of the structure. Thereby, we need to provide the sufficient amount of space. Let us say this we can actually relate with the bleeding in the asphalt mixtures. Though here we are talking about the concrete mixtures, let us discuss about the bleeding phenomenon in the asphalt mixtures. We have discussed that we are supposed to provide minimum few amount of air voids. What will happen if we don't provide the air voids? At least minimum amount. So during the summer, so whatever the binder that is present inside will not have the enough volume to expand. When it doesn't have enough volume to expand inside the bituminous mixture, that binder comes out of the asphalt pavements and you can see on the pavement itself a black kind of patch. That means it's a bituminous thick patch you can see, which is called as the bleeding. In the similar way, admixture is used because this actually provides a uniform, stable and teeny bubbles in the concrete. So it actually provides very teeny bubbles in the concrete. Thereby, the segregation of concrete can be avoided, workability can be improved, especially anti-freezing ability and durability of the structure can be enhanced. So one of the disadvantages is, let us say if your concrete is having more pores, let us say porous concrete, it is obvious that its strength would be reduced. Compared to the more compacted and solid concrete, if any of the concrete having the air or gaps inside that, it would definitely be having lesser strength. So how much is the strength is lesser? Let us say if I wanted to introduce this air entraining admixtures into the concrete, so by introducing 1% of air content, it will reduce the compressive strength by around 3 to 5%. So we have to design the concrete mixtures in such a way that it should always meet. Let us say if I am going to provide OPC 43, so I should have minimum of this compressive strength. But in addition to that, that means we can also compromise on few of the air voids, but still it should satisfy the compressive strength properties. And this entrained air usually provides space for freezing or expanding the water to prevent the cracking. And it is recommended that 0.001 to 0.1% by weight of the dry cement. So this much amount of air entraining admixture can be added. So another kind of admixture is the retarders. So to delay the initial setting time up to an hour. This we have already discussed in the last class. Let us say we have a ready mix plant or we have a plant at a distance of very long. So we are mixing the concrete here, but it takes a lot of time to reach to the site where we are actually going to lay the pavement. Let us say there is a 2 hours of time. So if we cannot able to maintain the concrete mixture in that plastic state, what happens? It will get solidified and it will get much setting and it will be very strong like solid by the time it reaches to the site. Thereby we need to maintain the plasticity of the concrete mixture. So these retarders, they usually delay the initial setting time up to an hour. These are especially used in the hot weather conditions because during the hot weather conditions we have higher probability of the water to get evaporated, thereby the cement gets setting very quickly. So how do we actually add these retarders? One of the way is we usually dissolve this retardant in the water, then we will spray on the surface of the concrete. So we have two ways. One is directly mix in the water and that water will be mixed with the cement and then produce the concrete. Another is after preparing everything, just spray on the surface. But just spraying on the surface would be one of the disadvantages because if you just spray on the surface, only surface would be in plastic state and only that surface would be retarded from the setting. Inside material will not be having the benefit. So these retarders, how do they actually work is, initially when I add the retarders, they absorb on the surface of the cement. So if you see any of the mechanisms in all of these admixtures and pozzolana, they initially go and they will be sitting around the surface of the cement particles, thereby it is forming the repulsive forces between the cement particles and thereby retarding the setting time or the reaction of the cement with the hydration or water. So these retarders at the end what they do? They actually adsorbs on the surface of the calcium hydroxide also. So when they absorb on the surface of the calcium hydroxide, they usually prevent the growth of the calcium hydroxide also. So it is recommended that 0.5% by weight of cementitious material. So when I say cementitious material, it is not just a cement. Let us say if I am going to add some fly ash along with the OPC, then the amount of cement present plus the amount of fly ash together is called as the cementitious material. Thereby 0.5 percentage of this cementitious material would be used as a retarder. So these are the kind of admixtures and also some pozzolanic materials. So there are few alternative cements which are called as the geopolymeric cement. So as we have already discussed, the main purpose of all these alternatives is we wanted to reduce the CO2 emissions. We know CO2 is inevitable. We cannot do anything about that. So we have the clinker and we will be adding the gypsum, and when it is under hydration, so it would be forming definitely which is called as calcium hydroxide plus CO2 plus CSH gels. We know this is the advantageous product. We wanted to avoid this because to prevent the sulfate attack, and we do not want the CO2 to be released into the environment because we know the global warming issue. Thereby, few of the disadvantages of OPC are we are actually using a lot of natural resources. Yes, because as the construction is increasing, we need this clinker or calcium aluminate raw materials. They generally are natural resources. So as we keep increasing the infrastructure, the natural resources are depleting. In addition to that, CO2 is also increasing. So we need the alternative materials, thereby we can actually eliminate these two disadvantages. So one of the option is geopolymer. So instead of using the raw materials for calcium or silicate related products, we have something called as solid aluminosilicate powder. Let us say this is a kind of inorganic some polymer. So this powder usually have to be activated by some other hydroxide which is alkali hydroxide. So if we have some aluminosilicate powder and if we can able to activate that using alkali hydroxide, then that can be used as an alternative to this cement. How? Let us see. The alkali activators, when I say, they are like sodium hydroxide, potassium hydroxide, for example. So this reactive aluminosilicates, for example, whatever the silicate powder I have observed, which is a inorganic polymer, that will be dissolved and it forms some free SiO4 and AlO4 units. So here what is happening? We have some aluminosilicate powder. This powder we will be dissolved into one solution. So preparation of this solution is also very important. The very accurate amounts of sodium hydroxide and the related compounds, a solution will be prepared, and this powder consisting of aluminous silicates. So this powder dissolves into the solution and it will form SiO4 and AlO4 units. So these units are very much important for us, because these units, when they are reacted with the oxygen, they will form a bond called as SiO and AlO bonds. So during this process, you also can observe that there will be an emission of water. So this water actually can be used for the workability. So as I was saying that this aluminosilicate powder is required. So we know we wanted to eliminate usage of raw materials. So how do I get these aluminosilicate powders? I should not use anything from the natural resources now. So these aluminosilicates are usually obtained either from fly ash, GGBFS, metakaolin and rice husk ash, etc. So we know these are the products from industry. These are not a natural resources. Thereby we are also utilizing the waste products from the industry, and also we are trying to provide a better cementitious properties. And we also told that this aluminous silicates needs to be activated by some alkali activators. So here we have provided few of the alkali activators. So what are the factors affecting the geopolymer properties? Let us say if I have some aluminosilicate powder and if I have the activators, so if I mix them with the solution, will I get geopolymers of same strength always? No. The strength properties of these geopolymers depends upon the ratio of SiO2 to Al2O3, that means silicon oxide to aluminum oxide, and other properties. So but currently we do not have a standard mixed design process to produce this geopolymeric cement. Though we have the literatures available, as people have been trying to understand its behavior, yet we do not have a standard like IRC 44 per OTC. Okay. So after discussing, so till now we have discussed about the types of cements. So when I say types of cement, we discussed about OPC and all the types of pozzolanic materials and the related cements. We also have discussed about the types of admixtures and their purposes and what is the use. So now let us move to the PQC, pavement quality control. For example, this PQC, which is the topmost layer on the pavement surface. Okay, this is the most commonly used for the pavement construction, and we try to use above M30 for the construction depending upon the purpose. It starts from M35 to M50, and the maximum aggregate size suggested is around 32 mm and with a low slump. Slump is an indicator of workability. If we have higher slump that means let us say slump is what? We actually prepare the concrete mixture and we try to keep that mixture into a cone type of material and we remove the cone. So after removing the cone, we see that the material will be falling. So you can see some material will be fall from the top. So if the material is very loose in state or it is in plastic state, we can see higher slump. If not, it will be in the lower slump. So we recommend to use the low slump with 32 mm maximum aggregate size for the PQC construction. And what are the main features to be understood while designing this PQC mixed design? One is the strength. We need to have the higher compressive strength. Let us say if I am designing my pavement for the compressive strength, then it should have the higher compressive strength. If my design is for the flexural strength, it should also satisfy the flexural strength. It's not the only criteria to be satisfied. In addition to the strength, we also need to satisfy the workability. So the workability would be in terms of slump we will be always measuring, and it depends upon the amount of water to cement ratio. And the third thing is durability. So whether it should be the sulfate resistant or not, how it is going to be sustained in various seasons. So these are the three parameters that needs to be understood while doing the mixed design of concrete especially. And another new term is characteristic term. For example, what is this characteristic term? If I have casted 100 samples, that means I have prepared 100 cubes of concrete. We know that, let us say I am aiming for M30, 30 megapascal strength. So sample 1, I got 32 megapascals. Sample 2, I got 25 megapascals. Like that, if you cast 100 samples will have some compressive strength. We cannot expect that 100 will be meeting all 30 megapascals. There are 4 samples which are having the strength less than 30 megapascals. Even though we are assuming the strength to be 30 megapascals, there are 4 samples who have only 20. That means their strength is less than 30. It is okay. So code says that we can actually allow 5% of the samples to be failed. So that means 95% of the time we should meet the compressive strength. So what is that strength? That strength, so that 5% of the material will never will be always only 5% is the maximum amount of the percentage material can fail. That is called as characteristic strength. Because all our design starts with the characteristic strength. So even though let us say my characteristic strength is 30 megapascals, I would not be designing for 30. We are supposed to design for higher reliability or some extra strength. So that we assume that considering all variability at the end, our material or pavement or concrete could able to take the real compressive or characteristic strength. So let us see the few steps of the mixed design of PQC. The first step is calculation of target strength. What is this target strength? Because my design must be for 30 megapascal. Let us say 30 megapascals is my expected strength. Yet I have to design for something more. Maybe 40 megapascals or 45 megapascals. I don't know what is that. So what is that extra strength? What is the total strength for which I have to decide? That is called as target strength. So how do we calculate the target strength? As I have already discussed, we can design this PQC either for compressive strength or flexure strength. When I say that we can design for anything, let us say if I have a slab, I can aim in such a way that this slab should not fail in the compression. That is one of the criteria. That means when I apply the load from top, I do not want any crushing here. I want my slab to be very stable. That is one of the criteria. And the another criteria is, let us say I do not want my slab to be bending like this. This is called as flexural criteria. So depending upon the purpose, if depending upon the load applications that my pavement is going to subject, sometimes we might design for both. So let us say if I wanted to design for compression, this is, if I want to design for tension or flexion, this is the criteria. So we can actually design for any of the criteria. Let us say if I am going to design for flexural criteria. So initially we have to calculate the target strength. So this F dash CR is called as the target strength. How do we get the target strength? Let us say this is your expecting compressive strength, or you can say that characteristic strength. So this characteristic strength plus we are going to take some extra provision or reliability 1.65 into SF. Here SF is nothing but the, that is a standard deviation. So this characteristic strength we already know, that is like depends upon our project or the load conditions, field conditions. So that we already know always. But how do we get this SF? So in order to understand the standard deviation, we already have a table. You can see this table. So this is the table for flexural strength. So what is given in the column 1, grade of the concrete according to the flexural strength. Let us say 3.5, 4, 4.5 to 5.5. So, and it is also given that according to the flexural strength, the assumed standard deviation is given. So if I know the, let us say if I know this FCR, I can calculate, I can select the SF. So if I can able to select that, then I can calculate the target strength. And if we wanted to design the pavement for, let us say, compression. So if we want to design for compression, let us say. So what happens in the compression also, we could see there is a table on the right side where M30, M35, M40. So these are the grades of the concrete and the corresponding standard deviation also given. So we have again two formulas, F dash CK, F dash CK. So these are the two formulas. Why they are given two formulas is we have to calculate this F dash CR from first formula, and also we have to calculate the F dash CR from second formula. So out of these two, whatever is the maximum value, we have to design for the maximum value. We should not take the minimum. We are taking here maximum because we are still going for the worst condition. And in the F-CK also we calculate based on the two formulas. In the F-CK, if you see in the second formula, you do not know the X or we do not know the SC. So we have the tables corresponding to the grade of the concrete. So we can actually select. So in the first stage, we have to confirm what is the target strength for which I am going to actually design my PQC is for. Let us say our target strength is already determined. So now in that concrete mixture, let us say 1 meter cube, in the concrete mixture of 1 meter cube, what is the amount of air present? We know that definitely there must be some amount of air that is entrapped. It will not be a 100% solid structure. So how do we calculate the entrapped air? This entrapped air depends upon the NMAS. You know that if we have more fine aggregate, there is a chance that smaller bubbles or airs would be entrapped in the in between. So if you see based upon the NMAS, you can have either 0.9 or 1 or it is the entrapped air as a percentage of volume of concrete. Into the volume of concrete, we assume in the mixed design is 1 meter cube. Let us say if my NMAS is 90 and then my amount of air that is entrapped would be 1%. That means 1 by 100 into what is the volume of the concrete? 1 meter cube. So this is the volume of entrapped air in the concrete. So now we have calculated the target strength and also we have calculated the amount of air. Let us say if my total volume of concrete is 1 meter cube, then minus.
This, excuse me, madam. This yeah, targeted strength is equals to um, how you did it? Targeted strength is equals to. Uh,
If you let us say
uh,
if we see here, sir.
uh,
So there are first two equations, sir. F dash here.
yeah, yeah.
So if we are designing for flexural strength, then F
Hmm.
dash here we are going to calculate. So on the right side we have FCR. So that means that is a flexural strength. So
Hmm.
let us say if I am going to design for flexural strength of 3.5.
What is this flexural strength and why
Flex,
it is required?
flexural strength is because concrete is actually strong in the compression, but the
Yes, yes.
concrete is very weak in the tension. When I apply the load, it will bend. So when we are going to design concrete, we have to design in such a way that it should able to take minimum flexural strength. It should not be like immediately it should bend. So if my load coming on the pavement is very less, then I can go for, let us say, in the left side table only 3.5 Newton per mm square. So this flexural strength depends upon the how much traffic is coming. If the traffic coming is more, then I have to choose higher flexural strength. Let us say if I choose lesser flexural strength of 3.5, then the corresponding standard deviation is 0.35.
Okay.
So in the equation then FCR is 3.5 plus 1.65 into SF would be 0.35.
Okay.
So
Standard
that's
deviation.
standard deviation. So in the
Hmm.
same way, we have another formula F dash CR equal to FCR plus 0.55. So
Hmm.
here directly we can substitute FCR is 3.5 plus
Hmm.
0.55. Now we will get two target strengths. One
Hmm.
F dash here belongs to another. So out of these two, whatever is the maximum, we have to select that one.
Okay. Okay.
In the same way, for compressive strength also we can do.
Hmm.
And if we proceed to the third step, so let us say In the second step, we have
This
calculated the,
entrap in this entrap in this
uh,
entrapped here, this 1 by 1,000 1 m cube, you don't you put its weight 2,450.
no, currently we are just calculating the volume, sir.
Hmm.
We are not going to calculate the weight because
Okay.
weight of the air would be zero, so we don't need to calculate that.
Acha, acha.
So it's always
Okay.
volume.
Hmm.
So in the second step, we will be calculating the entrapped air. So as I have already discussed, let us say if my NMAS is 19 mm, then the entrapped air would be 1%. That means 1%, 1 by 100 of what is the volume of the concrete? 1 meter cube. So this is what the volume of the entrapped air. So out of total 1 meter cube of concrete, 1 by 100 of 1 meter cube would be air. That means the remaining would be the solids. So we will
Means
discuss.
for every 1 m cube of concrete, this is the quantity of entrapped air we can say.
Yes, sir. For every 1 meter cube, 1% is the entrapped air if the NMAS is 19 mm.
Okay, okay.
So based on that, whatever remaining volume would be the solid volume. In that solid volume, the proportion of cement, aggregate, all those can be calculated. So if we proceed further, as we have already determined the target strength, we need to select the water to cement ratio. This is actually the main parameter in the mixed design. So how do we select the water to cement ratio? Let us say if I am designing for flexural strength and my flexural strength is 4 Newton per mm square, let us say, and if I choose OPC 43 or 53, I am going to choose, let us say, OPC 43. So if I choose OPC 43, then 0.46 would be my water to cement ratio. This is a direct value. And if I am going to design for compressive strength, and this is my compressive strength, let us say 58 at after 28 days, then if I am going to choose again OPC 43, then my water to cement ratio would be 0.3. So after selecting our water to cement ratio, you can see that the maximum water to cement ratio in the table you can see is always 0.5. So we should not have more than that.
Okay, madam, one thing is that how is flexural strength is correlated with the compressive strength? How do you relate that? Say if a flexural strength is 7, so what should be the grade of concrete?
Yes, sir. So usually we have an empirical relation. So zero point 0.7 to zero point 0.8 into root FCK. Let us say, so if
This
you know,
FCK is a characteristic strength.
yeah, characteristic strength. So this is
Okay,
the characteristic strength. If we know the characteristic strength, we can calculate the compressive strength from the target strength.
correct.
So this is usually we take 0.75 times. That means we assume that if the any concrete or mixture is having 100 as the megapascals of compressive strength, 70 would be the flexural strength. That means if any of the concrete is going to fail by 100 megapascals load, then in the flexure it can't able to take the 100 megapascals. It takes only 70%, 70 to 80% of the load.
Hmm. So if in that case say M35 grade is concrete, that 35% of the M35 is flexural strength.
We
Say,
cannot we cannot directly say because M35 means that is a compressive strength. So
ah,
from
ah.
that we have to calculate the characteristic strength and then we can. So for our understanding, we can say around 70 to 80 percentage of compressive strength would be characteristic strength would be the flexural strength.
Okay.
So once if we determine the water to cement ratio, it is very easy to calculate the water content. Let us say I know water to cement ratio is, let us say, 0.5. So if I wanted to know the water, what I have to do? Water content would be zero point 0.4 into cement content. Okay, so this so we can usually calculate. So let us see here. So there are few tables. Let us say this is a table where NMAS, nominal maximum aggregate size, and also the suggested water content. So if my NMAS is 19 mm, So they are suggesting that directly you can take 186 kgs per metric cube as a water content. But there is a condition that this table is applicable only for a slump of 50 mm and for the aggregates which are angular in nature. That means, let us say we know we have different types of aggregates. One is rounded aggregates, and there would be subangular aggregates and etc. So what is the difference? If the aggregates are rounded, we need lesser water content. If the aggregates are subangular, we need lesser water content. If the aggregates are angular, we need more water content. Because angular aggregates, when you are going to mix, they are very difficult to mix, so they need more lubrication. So we need higher water content.
Less workability.
Less workability. So if we have subangular aggregate, we have to reduce the water content by 10 kg. For example, if I choose my water content as 186, this is for angular aggregate, but my aggregates are, let us say, subangular, then I have to reduce 10 kgs, which is nothing but the 176 kgs would be my water content. If we are using gravel, then we have to reduce the 15 kgs, and if you are using some crushed particles, 20 kgs. So we have specifications for different kinds of aggregates. And in addition to that, we also have mentioned that this table is applicable for 50 mm slump. That means very loose mix, we have this much 186 is the water content. Let us say if I don't want to produce a slump of 50 mm, I wanted to produce a slump of 25 mm. That means a kind of stiffer material. Then I don't need to add the higher amount of water. I need to reduce the water content. How much we have to reduce? So according to the specification, 3% for every additional 25 mm. So if 186 is the water content, now I have to reduce 3%, 3 by 100 of 186 for every 25 mm slump reduce. And if you are going to use plasticizers, then you have to reduce 5 to 10%. If you are going to use super plasticizers, again you are going to reduce. So once if we understand how to calculate the, now we know the characteristics, target strength and air entrainment, and also we have calculated the water to cement ratio. We need to select the cement or cementitious materials. So this minimum cement or maximum cement are the conditions we have. Let us say 360 kg per meter cube is the minimum cement that we have to produce irrespective of the any of the proportion. And maximum should be 450 kg per meter cube. So after calculating all the proportions, we need to make these checks. And if the fly ash is blended at site, not more than 25% should be used. Minimum cement content should be 310 and for fly ash and 250 for GGBFS. Okay, so these are if we use separate pozzolanic. If you are going to use OPC, the minimum is always 360. So after obtaining the cement content and water cement ratio, the proportions of coarse aggregates and fine aggregates are a major thing. Let us say if we have NMAS of 19, nominal maximum aggregate size of 19, and this zone 1, 2, 3 are actually for fine aggregates. Zone 1 is a kind of higher coarse, zone 2 little finer, zone 3 will be more finer. So let us say, usually we decide, let us say I am going to use the fine aggregates from the zone 2, then my nominal maximum aggregate size in the coarse aggregate is 19. Then we have to select 0.62. That means let us say total 100% is the aggregates. Out of this 100%, now 62% would be coarse aggregates and remaining whatever 38% would be fine aggregates. So if your nominal maximum aggregate size is 31.5 and if you are going to use zone 3 fine sands, then 68% would be coarse aggregates. 100 minus 68 would be, I think 32 is the fine aggregates. So this is how we are going to calculate the proportions. But this table is
where is all summaries? Where is this all written? This summaries in
IRC. So all these things, tables and the details. IRC 44 2017. This is a free document. We can actually download this in the Google. So all this in the summary table form will be available in this code book.
Okay.
So this table is actually for water content of 0.5. But we know that every time we are not going to produce a mix for 0.5. And also this table is for SST aggregates. That means aggregates which are having absorbed water inside but there is no water on the surface. But if we wanted, and also for angular aggregates. So this table is exclusively for these three conditions. So in the concrete mixture, if any of our aggregates doesn't have these properties, that means water cement content is ratio is not 0.5, or they are not SSD aggregates if they are dry aggregates, and those are not angular aggregates, they are, let us say, subangular. Then accordingly we have to change our coarse aggregates. How do we change? Let us say if water to cement ratio is, let us say, SSD aggregates, instead of that I wanted to use dry aggregates. Then I have to actually remove whatever is the extra water content that is absorbed. Then how are we going to change the coarse aggregate proportion? So those are the calculations that we will see in one of the problem. Let us say, for example, here, for every decrease in the water cement ratio by 0.05, let us say if the water cement ratio is reducing 0.5 minus 0.05, that means water to cement ratio is reducing to by 0.05. That means your water is, let us say, reducing. Then if the water is reducing, coarse aggregate should be increased. Why? If the water amount is less, fine aggregate amount would be less. If the fine aggregate amount is less, out of 100% of aggregate, if the fine aggregate percentage is reducing, means coarse aggregate should be increased. How much we have to increase? They are saying that for every 0.05 reduce in the water content, we have to increase this 0.01 meter cube of coarse aggregates. We also will discuss this in one problem so that we will get more clarity. So till now whatever we have discussed or calculated are volumes. So these volumes, if we wanted to calculate the weight, we can calculate using the specific gravity, because we know specific gravity equal to weight by volume. So if we wanted to calculate the weight, we need to multiply these volumes with the specific gravities. We need to make sure that every time when I am taking the specific gravity of water as 1, this is in terms of gram per cc. Okay. Then we are supposed to convert this gram per cc into kg per meter cube. We should not forget this. So once I have decided all my coarse aggregates, fine aggregates, cement, water and water to cement ratio, now I have to make a trial mix. So let us say I have decided some water to cement ratio of, let us say, 0.42. Then I got coarse aggregate proportion, fine aggregate proportion, cement and water. Using all this, I will mix few trial mixes. Then what I have to aim for, first is the slump, target strength. So this slump is for the workability. Let us say if I am aiming for 90 slump. After producing the mix, if I could able to meet the 90 that is fine. Then I will use the specimens again for the targeted strength. That means I use the specimens to test, apply compressive strength, and I try to see how much strength it is actually able to take. If it could able to satisfy all our requirement, then I can say these proportions are correct. If not, then again I have to make another trial with another water to cement ratio. If I change this trial, then maybe other proportions can also change. In this way, usually this mixed proportion would be changing. So let us quickly discuss about the one problem, and later we will see few numericals, few theoretical and other numericals. So this is the one of the problem where, so details given are, we have to design for a flexural strength of 4.5 Newton per mm square, and the type of cement to be used is OPC 43, and they have provided the nominal maximum aggregate size of 31.5, and they are also asking us to maintain the workability to around 25 plus or minus 5 mm, and the aggregates used are crushed angular aggregates. Super plasticizers to be used at 1% by weight of cement. And in addition to that, the specific gravity per cement, coarse aggregate, fine aggregate, and also super plasticizers are given. And the water absorption of coarse aggregates and fine aggregates are given. It is mentioned that there is no surface moisture in the aggregates, and zone 2 sand is used. So if we have given with this information, we know our first step would be always to calculate the target mean flexural strength. So what is the formula? F dash CR equal to this. This is one of our formula, and this is another formula. So in the second formula, we can directly substitute 4.5 plus 0.55, we get 5.05 megapascals. But in order to calculate in the first equation, we need SF. How do we get the SF? We have a table corresponding to the FCR and SF. So currently we have to design for 4.5 flexural strength. So the corresponding SF is 0.4. So 4.5 plus 1.65 into 0.4, then we got what is called as 5.16. So one is 5.05, another is 5.16. So maximum of these two would be 5.16. So 5.16 is our target strength for the design. So once we calculate that, the second step would be to calculate entrapped air. So we know that this entrapped air is a function of nominal maximum aggregate. We have a NMAS of 31.5. So corresponding to that, the entrapped air percentage was given as 0.8. That means 0.8 by 100 into what is the volume of concrete? 1 meter cube. So which is nothing but the 0.008. So we will use this in the later stages. For now, keep this aside. So in the third step, we have to calculate the water to cement ratio. So this water to cement ratio is a function of flexural strength, target flexural strength, and also grade of the concrete. Let us say my flexural strength is 4. What was the flexural strength? We got target strength 5.16. So let us see here. For corresponding 5 target strength, for OPC 43, the value is given as water to cement ratio as 0.34. But for 5.5, it is given as 0.28. But our value of FCR is what? 5.16. That means in between these two. So then we have to do the interpolation. How do we do? On y-axis and the target flexural strength on x-axis. So for 5.5, this is from table. At 5, we already have some water to cement ratio. For 5.5, we already have some water to cement ratio. But at 5.16, we don't know what is the water to cement ratio. So we have to calculate that one. So using the similar triangles, we can actually calculate that. And we got the water to cement ratio as 0. So we also have to check that this 0.32 should be less than the water to cement whatever is provided by the code. As it is less, then fine. So once if we know that, the another component would be water content. Again, this water content is a function of nominal maximum aggregate size. So our nominal maximum aggregate size is 31.5. Corresponding to that, it was mentioned that 165 kg per meter cube would be our water content. But this table is for the slump of 50 mm and when there is no admixtures. But here in our case, the slump is 25 mm. That means we have to now reduce our water content. How do we reduce? We know that for every decrease in 25 mm slump, we have to reduce the water content by 3%. Okay. So 165 is for 50 mm. So 165 minus 3% means 3 by 100 into 165. We get around 160 kg per meter cube if our slump is 25 mm. Some correction. But we are going to use the plasticizers in our case. If there are no admixtures, then the above table will apply. If you are going to use the plasticizers, that means in the given water content, around 20% we have to reduce. If the 20% is reduced means we have to use only 80%. So 0.8 into 160, that means finally our water content would be 128 kg per meter cube. So if we know the water to cement ratio as 0.32, if we know the water as 128 kg per meter cube, so we know water to cement equal to 0.32. You know the water, you know this value. So we need cement. Cement would be 128 by 0.32, which is nothing but the 400 kg per meter cube. Here we have to check We have a minimum cement criteria of 360. Yes, our value is more than that. And also maximum of 450. Yes, our value is less than that. Thereby we can proceed further. So now we have to calculate the volume of coarse aggregates and fine aggregates. And we know that this coarse aggregates fine aggregate fraction is a function of nominal maximum aggregate size and also the fine aggregate zone. Here in the question they have mentioned that we are going to use zone 2 sand and our nominal maximum aggregate size is 31.5. The corresponding value of coarse aggregate fraction is 0.65. So this table is for SSD condition and this table is applicable for water to cement ratio is of 0.5 and for angular aggregates. But in our case the water to cement ratio is not 0.5. It is less than 0.5. So how are we going to reduce our water to cement ratio? First we have to calculate how much water content we have. Let us say 0.5 is table is given for 0.5 but we have 0.32. So 0.5 minus 0.32 is what? Our extra water content, water to cement ratio. So that extra water to cement ratio. But code suggests that if you have 0.05 extra, then you have to increase the volume by 0.01. So for 0.05 extra water to cement ratio, you have to increase 0.01 percentage of coarse aggregate. But currently I have 0.5 minus 0.32. This much amount of water to cement ratio is extra. So how much I have to use? So if you multiply, so you will get directly 0.5 minus 0.32 into 0.01 divided by 0.05. That is what I have directly written here. So finally if we calculate, we got 68.6. That means coarse aggregate proportion is 68.6 and the fine aggregate proportion would be 31.4%. And the next step would be to check for the combined grading. So usually, so for PQC design, just like let us say in the asphalt mixtures we have BC2, let us say we have mid gradation. So our gradation, whatever we are going to propose should actually satisfy the mid gradation. In the same way for PQC also, we have to confirm that the gradation whatever they are providing for coarse aggregates and fine aggregates, they should satisfy according to this. That we cannot do anything here, we need to make sure that. But the main step next would be mix calculation. Now we have to calculate the volume of cement because till now we came to know the percentage of coarse aggregates, percentage of fine aggregates. So let us calculate the real percentage or real volumes of cement, concrete and the cement water in the concrete. So we know that the 0.08, 0.008 is the entrapped air. So out of 1 meter cube of concrete, 0.008 is the air. So I will remove that air, then whatever is left, which is nothing but 0.992 meter cube, is the only concrete. So out of this concrete, we will be having cement, aggregates, water, all those things. So let us say volume of cement if I wanted to calculate, we already calculated 400 kg per meter cube as the required cement in kgs. So if we divide that with the specific gravity, we got what is called as 0.127 metric cubes of volumes of cement. In the same way, volume of water was 128. Then we can calculate from that kgs to volume here. So if you also see here, it was mentioned in the question that we have to use super plasticizer of then 1% by weight of cement. That means 1 by 100 into weight of cement is 400. So we also have calculated the volume of super plasticizer. So now what are the volumes of aggregates? So this is actually the total concrete volume after removing the air. So in this total volume of concrete, let us remove the volume of cement, volume of water, volume of plasticizer. So whatever is remaining is actually the volume of aggregates. So in this volume of aggregate, as we have already calculated the percentages, So 68.6% of this value would be coarse aggregates, 31.4% of that value would be your fine aggregate. So 68.6% of this into specific gravity, you will get the kg per meter cube. Same if you do fine aggregates. So finally we got the cement, water, coarse aggregate, fine aggregate, super plasticizer and water to cement ratio. This is the initial trial, let us say. So these are all in SSD condition. That means if you use the aggregates which already have absorbed water, then these are the proportions. That means in these aggregates actually there is some amount of water already inside the aggregates. So whatever the water I am going to add, that would be extra. Okay. Let us say if I in the present question, they have already given the water absorption for coarse aggregates and fine aggregates. So if I wanted to do these proportion calculations for dry aggregates, that means there are some dry aggregates plus and some, let us say 0.5 percentage is the water absorption. So 0.5 percentage of this dry aggregate. Currently I am calculating for, let us say, coarse aggregate. So dry aggregate plus 0.5 percentage of dry aggregate together is what? Our SSD coarse aggregate weight. So till now whatever the weight or volume of coarse aggregate I have calculated is this SSD coarse aggregate. So this is actually dry aggregate weight plus water absorbed equal to this. But I do not want, so I wanted to calculate what is this dry aggregate. So we can easily calculate. So here X is the dry aggregate. So if we calculate 1372, that means till now the value of coarse aggregate equal to 1379 kg per meter cube. But in the dry state, it is 1372 kg per meter cube. That means whatever this difference 7 is there, that is actually water. Okay, that means inbuilt there is 7 water, 7 kgs per meter cube. For every meter cube, there is 7 kgs of water. Okay, in the similar way, for fine aggregates also, if we calculate, we got that around 6 kgs per meter cube is the water. For coarse aggregate, 7 kgs per meter cube is water. So, what is the total water content? 128 plus 6 plus 7. So, total is 141. So, if I don't add this 6 plus 7, that means we assume that we have lesser water content. But usually we have more water content which was in inbuilt 6 plus 7 also there. So, I am going to add that also. So now because we have more water content considering the water absorption also, if the water content is changing, then how do we calculate water to cement ratio? So if we know the new water content, let us say 0.43 is my water to cement ratio. Now my water content is changed to 141. So then my cement also will change correspondingly. I will calculate my cement content. Then I will follow with my coarse aggregate proportion, fine aggregate proportion, all those things. Same thing. Then we'll check for the slump. Then if the slump is satisfied, then again we'll go for the strength. If the strength also satisfied, then we'll say that this is my final proportion. If anything is not satisfied, then again we have to do another trial. So what we are going to do is, let us say I have done multiple trials like water cement ratio. Let us say 0.42, I have done one trial. Then I got some flexural strength. Here, okay. Again, something more than 0.42, I have done another trial. I'll get another flexural strength. Less than 0.2 water content, I have done another trial. So I will get some curve, right? Let us say 3 points are there. This is the water to cement ratio and this is the flexural strength of 28 days. So based on this, then we can choose the satisfying 28 days target strength. So let us say if we have a curve, in this curve, let us say I wanted to design my concrete for this strength. Then directly from there I can take the corresponding water content ratio. So in this way usually we calculate. Let us say if I wanted to make some changes, like I do not want to use only cement. In addition to that, I wanted to add fly ash of around 20%. Okay. Water to cement ratio is 0.32. Cement is 400 kg per meter cube. So now what we have to do? If we use any admixtures, we have to increase 10% of cement. So when I say 10% cement should be used, that means now we have already cement of 400 kg per meter cube. This is 10% should be increased means 1.1 into 400. That is what I have calculated here. So 440. So it was mentioned in the problem also that 20% is the fly ash. So 20% of what? 20% of total cement. So out of this 440, 20% of that. That means 88 kg per meter cube is our fly ash. So in the OPC, so total 440 is our cement minus 88 is our fly ash. So whatever remaining would be, we have to make sure that that should satisfy our minimum and also maximum criteria. What is the minimum here for fly ash? 310 is the minimum. Maximum should be 450. So if we calculate the new cement, we also have to calculate the new water to cement ratio because water is 128. Now the cement is 440. Thereby from this we will get the water to cement ratio. And we have to make sure that that water to cement ratio is less than maximum water to cement ratio of 0.4. Okay, let us quickly look at the another problem. Let us say it was given that we need to design M40 with OPC 43. That means here we are going to design for compressive strength, not the flexural strength. NMAS of 19 mm is given. Workability is same, 25 plus or minus 5. And the crushed angular aggregates are going to be used. Super plasticizer we are going to add. These are the specific gravities and water absorptions. And it was mentioned that it is a zone 2 sand. And on the surface of the coarse aggregates, there is no free moisture because 0%. But on the surface of fine aggregates, there is some free moisture of 4%. 4%. So as we know, always the first step is to calculate the target strength. So we have these two formulas. So if you see the first formula here, so we know the grade of the concrete is M40. The corresponding SC is 5 from the table. So you can directly substitute that. And another formula is grade of the concrete is M40. The X would be 6.5. So we can substitute in these two. Then we got 46.5 megapascals as one of the characteristic and another is 48.25. Out of these two, the maximum is 48.25. And in the second step, it was given that the NMAS is 19 mm. So directly for the NMAS 19 mm, 1% is the air trap. So 1 by 100 of 1, which will be 0.01 meter cube. And in the third step, we have to calculate the water to cement ratio. This is again depends upon the characteristics and also the grade of the cement. So this F-CK we have already calculated previously. It was coming 48 and OPC they have mentioned was 43. So our value will be 0.36 and this is less than the maximum value. So it will be okay. And if we wanted to calculate the water content, it again depends upon the NMAS of 19. So for the 19, corresponding water content was given as 186. But this is for the slump of 50 when there is no admixture. But in the current, we are going to actually add super plasticizer and also our slump is 25. So from the 186, first we have to reduce 3% of 186. This is for the slump correction 25 mm. And out of that 180.4, now we have to take only 80%. That means 0.8 because 20% we have to reduce because we are going to add super plasticizers. Thereby, our total water content is 144 kgs. So, if we know the water to cement ratio and water content, we can calculate the cement which is 400 and again it satisfies the minimum of 360, maximum of 450. Now we have to calculate the coarse aggregate proportions. So how do we calculate the coarse aggregate proportions? We know that our NMAS is 19 mm and our fine aggregate is from the zone 2 sand. And this table is for water content of water to cement ratio of 0.5. So let us choose this value first, 0.62. But we have the water to cement ratio different. How much different? 0.5 minus 0.36 different. So for every 0.05, we have to increase to 0.01. Then we have to multiply this. Thereby, we got coarse aggregate percentage as 64.8, fine aggregate as 35.2. So checking gradations, here anyway, if they provide, we have to check for gradation. And all the proportions that we have got are for SST condition. We should not forget that all the tables are for SST condition. So we have to actually calculate for the dry conditions. How do we calculate? First, let us calculate the absolute volume of concrete. Out of 1 meter cube, we have to remove this air, whatever is entrapped. Then the remaining 0.99 would be the absolute volume. So let us calculate this volumes of cement, water and superplasticizer. Cement, we know that 400 kg per meter cube. So when we divide with the specific gravity, we get the volume. In the same way, water, when we divide with the specific gravity, we get the volume. For the superplasticizer also, when we divide with the specific gravity, and we are going to use 1% of weight of the cement, that is 400, and we are dividing that with the specific gravity, then we are going to get the volume. So out of this much solid volume of 0.99, we are removing the cement, water and also superplasticizer. Then whatever is remained, that would be our only aggregate proportion. So in this aggregate proportion, as we have already determined this percentage, 64.58 would be coarse aggregate, 35.2 would be fine aggregate. So how do we calculate the weight? So this 64.8 means 64.8 by 100 out of this solid volume into specific gravity, you will get the weight. In the similar way, we get the weight of, and in the similar way, we get the weight of fine aggregates also. So whatever the weights we have calculated till now, these are for the SSD condition. Let us say I wanted to calculate those for the dry condition. How do we calculate? So we already know, like in the previous discussion. So for every let us say, so 1271 is what previously we have coarse aggregate. So now we have to actually reduce or increase the coarse aggregate based upon the condition. Let me see here. So whatever till now we have is the wet aggregate weight. That means that absorption of 1% is included and also the surface moisture of 4%. So this total 5% is increased. So as you have seen previously, this dry aggregate plus the percentage of water into dry aggregate is what we are going to get the wet aggregate weight. Okay. So from this we have to calculate the, so let us say previously what we got coarse aggregate is 686. So you will be calculate 686 kg per meter cube. And this percentage, you know, the 1% plus 4%, then you have to calculate this dry aggregates. So in the similar way in the previous problem, I calculated the using the same formula. This is the coarse and fine aggregate. So how much is that water content? Let us say when we have wet aggregate, the weight is 686. When we have SSD, that means that without the surface moisture, this is 660. That means 26 kg per meter cube is the extra water. This is per coarse aggregate. So what we are going to do now? Our total water content is 144. Okay, from this, whatever this extra water content we have to remove. Because without knowing that there is already this much of water, we estimated that we need 144. Now we don't need to add 144 because already there is an existing 26. So let us remove that. That is one condition. Plus And for coarse aggregate, we estimated 1271, but 1265 is what the required. So when we do this reduction, finally water we get is 124 kg per meter cube. That means initially when we have 144, finally it came to 124, as because coarse aggregate and coarse aggregate has some absorbed water inside, and fine aggregate has both absorbed and also free moisture. So based on the discussion till now, let us see few questions. Okay. Which of the following in pozzolana will react with calcium hydroxide to form cementitious materials? So if we wanted to form cementitious materials, the raw material should always be either siliceous or aluminous. Both A and B. Which type of cement is suitable for sewage treatment? So usually this sewage treatment works are always in contact with water. So as we have discussed, whenever the structure is in contact with water, there is a higher chances of sulfate attack. So in those situations, it is always preferable to use sulfate resistant cement or concrete. Okay. Which type of cement is suitable for sewage treatment, which is SRC? With the addition of silica fume in the cement, the water demand of concrete. So we know that silica fume is having the surface area higher than the, which is 100 times higher than the cement. As the surface area is more, it requires more amount of water to provide the required workability. Therefore, the addition of silica fume will increase the water demand in the concrete. Of course, we are not going to add that much amount of water. We are going to either use plasticizers or super plasticizer so that we can reduce the water demand. But in general, we require more amount of water. Which of the following arrangement in terms of size is true? We know that silica fume have higher surface area than cement. In between, we also know that there is metacoelin, which is having the surface area in between silica fume and cement. Then the option would be silica fume greater than metacoelin greater than. Okay, they are asking in terms of size. That means size less means surface area is more. So silica fume is lesser size. Then metacoelin is a bit more size, and fly ash is a bit more size. And if they also give cement will be a bit more size than these three. Air entraining admixtures are suitable for which type of climate? So the main purpose of air entrainment is we are going to provide few spaces so that during the freezing thawing cycles, that means when it is very cold and when it becomes liquid during summer, we have to provide a sufficient amount of volume. So in order to facilitate that volume of space in the concrete during the freezing and thawing conditions, we use air entraining admixtures. In geopolymer concrete, the alkali activators are used to activate. So how do we actually work with these geopolymers? We have some aluminosilicate powder. This aluminosilicate powder needs to be activated with the alkali activators. Then it actually reacts with the calcium hydroxide. So thereby here the option would be B. Okay, aluminosilicate. Aluminosilicate. The amount of entrapped air to be considered in the mixed design of concrete is a function of. So if you could have remembered while solving the questions, so in order to calculate the air entrapped, this is actually a function of NMAS, nominal maximum aggregate. Option C. The suggestive water content as per IRC 44 is 186. If the aggregates are subangular and the target slump is 25, what should be the water cement ratio? So they have given that 186 is the water content, but that according to the table. We know that the table is applicable only for 50 mm slump. So they are informing us, and the table is also applicable only for angular aggregates. So if the aggregates are subangular, actually we have to reduce the water content by 10 kgs. Then it will be 176 kg per meter cube. And also that table is applicable only for 50 mm slump, but here the slump is 25. If the slump is 25, we have to reduce. Then what we have to do? We have to reduce around 3 percentage. You can see here the, let us say 86. We have to reduce 10 kgs because the aggregates are subangular. So then you got 176. From this 176, we have to reduce 3% because our slump is now 25. So finally, option would be 170.7. So when fly ash is used for the PQC, minimum cement content as per IRC 44 is 360. So if it is fly ash, it is actually 310. If it is a OPC, then it is actually 360. If it is a fly ash, it will be 310. As per IRC 44, maximum water cement ratio should be, if you see the table, it will be mentioned that it is 0.4. So these are the few of the numericals from the week 11 lectures. So if you have any questions, you can ask. Otherwise, we will close the meet. Okay, then let us close the meet.
Ma'am, what are the uses of PSC cement?
Portland.
Ma'am, what are the uses?
Oh, these Portland cements or pozzolana cements, all of them are to avoid one is the environmental emission. Let us say in the OPC cement we are having CaOH5, calcium hydroxide. So we have an excess cement. We have to reduce that. So if we are going to add this pozzolana materials, they are going to react with the calcium hydroxide and they will form the CSH gels. Those gels are actually giving higher properties. That is one of the advantage. Another would be, let us say sometimes we do not want to use the natural resources like calcium silicate because they are always depleting in the nature. If we wanted to go for some industrial products like fly ash and blast furnace slags, from them also we can get the same cementitious properties. So one is to avoid the usage of natural resources, another is to reduce the calcium hydroxide production. We can actually replace them with the either Portland or pozzolana, blast furnace slag. All of these are of different various kinds of the pozzolanic materials.
Ma'am, where we use it? Marine
Oh.
structures or sewage treatment works?
Mostly in marine structures they are actually used, but even in the normal structures also we can use them.
Ma'am, in sewage treatment works, what we use?
Because in sewage treatment sulfate attack would be more predominant, so sulfate resistant cement would be more preferable usually.
Okay.
Okay then.
Ma'am, according to Indian specification, percentage of GBFS in PQC layer.
Okay. What was the?
Yes, ma'am.
What was the question?
Ma'am, according to Indian specification, percentage of doses of GBFS in PQC layer.
So those percentage limits you can check actually in the Google if you type for IRC 44 2017. So you will get a Indian Road Congress document. So this document will give all the limits for GGBFS, PSC, all the limits. You can check from there. You don't need to remember them actually. They are empirical values.
Okay, ma'am. Ma'am, water cement ratio? How? Hello.
Hello. Yeah. You are audible.
Ma'am, how we calculate the water cement ratio for OPC?
Yeah. Regarding that, we have a detailed discussion in the today's video only. So this recording I will upload. Maybe you can watch. So we also have discussed two problems of how to calculate water cement ratio.
Okay, ma'am. Thank you, ma'am. Thank you.